Welcome to this lecture on the properties of the sum function. Imagine you are building a complex machine, like a car engine, out of many small, perfectly manufactured parts. If you assemble them smoothly, the engine runs perfectly. In mathematics, we do something very similar when we add up an infinite number of functions. Today, we will explore the mathematical rules that tell us exactly when a combined sum function safely inherits good qualities, like continuity, from its individual building blocks. Now that we understand the goal, let us look at how these functions combine. Each individual function might be beautifully smooth and continuous on its own. But if the way they add up is uneven or chaotic, the final sum function might suddenly break or jump. We need to know under what conditions the final combined function retains the ability to be continuous, integrated, or differentiated. This is where the properties of the sum function become absolutely essential. Let us start with the most fundamental property, which is continuity. Continuity simply means you can draw the graph without lifting your pen. If we have an infinite series of continuous functions, the magic ingredient required to keep the sum continuous is called uniform convergence. This means the infinite series approaches its final sum function at a consistent, even speed across the entire interval. If you add up smooth curves evenly, the final combined curve is guaranteed to be smooth. To see how this works mathematically, let us look at the formula for the sum function. The capital S of x represents the final sum function we get after adding all the infinite pieces together. The lowercase f sub n of x represents the individual building block functions. We also define a partial sum, capital S sub n of x, which stops at a finite number of terms. Because adding a finite number of continuous functions always gives a continuous result, the partial sum is always continuous. Now that we have our formula, let us prove that the infinite sum is continuous at a specific point C. We must show that the difference between S of x and S of c becomes incredibly small as x gets closer to c. In mathematics, we represent this incredibly small distance with the Greek letter epsilon. We use a famous technique called the epsilon over 3 argument. By taking a detour through our finite partial sum, we use the triangle inequality rule. This rule states that the direct path between 2 points is always shorter than or equal to a path that takes detours. This breaks the total distance into 3 smaller manageable steps, setting up the foundation for our proof. Let us evaluate these 3 pieces to complete our proof. The first and third pieces represent the gap between the infinite sum and the finite sum at different points. Because the series converges uniformly, we can make both of these gaps strictly smaller than epsilon divided by 3 for all points at once. The middle piece is the gap between the finite sums. Because the finite sum is already known to be continuous, we can make this gap smaller than epsilon divided by 3 just by keeping x close enough to c. Adding these 3 tiny gaps together gives us exactly epsilon. We have successfully proven that the sum function is continuous. To truly understand why this proof works, let us look at it visually. The shaded tube represents our tiny error margin, epsilon, around the final sum function. Because the convergence is uniform, the entire graph of the partial sum eventually gets trapped inside this tube and never leaves it, no matter where you look on the horizontal axis. This strict trapping mechanism is exactly what forces the final sum function to behave nicely and stay continuous. Now that we have proven continuity, we can look at the next major property, which is integrability. Integrability asks whether we can find the area under the curve of our infinite sum function. Specifically, we want to know if we can just find the area under each individual building block function first and then add all those areas together. This is known as term-by-term integration, and it requires uniform convergence to work safely. This formula represents the property of term-by-term integration. On the left side, we are adding up all the infinite functions first to get the sum function, and then taking the integral from point A to point B. On the right side, we are taking the integral of each individual function first and then adding up all those infinite areas. If the series converges uniformly, these two sides are perfectly equal, allowing us to swap the integral and summation signs. Let us see this formula in action with a practical example. We will start with a very famous infinite series called the geometric series. A geometric series is a series where each term is multiplied by a constant factor to get the next term. We are given the geometric series for the function 1 over 1 minus x. Because this series converges uniformly on any closed interval strictly inside -1 and 1, we are legally allowed to integrate both sides term by term. We set up the integral from 0 to a variable t on both sides of the equation to begin our calculation. Now, we will use the powerful property of the sum function we just learned. We will swap the integral sign and the summation sign on the right side of the equation. By moving the integral inside the infinite sum, the problem becomes incredibly easy. Instead of trying to integrate an infinite series all at once, we only have to integrate the simple power function x to the power of n. On the left side, the integral is a standard calculus rule that results in the negative natural logarithm. By performing these basic calculus steps, we successfully discover a brand new infinite series formula for the logarithmic function. Having successfully integrated our series, we arrive at the final major property, differentiability. This deals with finding the slope or rate of change of the sum function, and it is the strictest property of all. Just because a series converges uniformly does not guarantee you can differentiate it term by term. The original functions must be differentiable, and crucially, the infinite series of their derivatives must also converge uniformly. Let us look at the mathematical representation of this strict rule. The left side shows us taking the derivative of the entire completed sum function with respect to x. The right side shows us taking the derivative of each individual piece first and then adding all those slopes together. When the strict conditions are met, we are allowed to swap the order of the derivative and the infinite sum, breaking down complex problems into simple ones. Let us try another example, this time using the differentiability property. We will use the exact same geometric series as before, but this time we want to find an infinite series that represents the function 1 over 1 minus x squared. Our strategy will be to take the derivative of both sides of the geometric series equation. Because the series of derivatives also converges uniformly for values strictly between -1 and 1, the strict rules of mathematics permit us to differentiate term by term. We apply the derivative operator to both the sum function and the infinite series. According to the property of term-by-term differentiation, we can move the derivative operator inside the summation sign on the right side. This means we just need to find the derivative of x to the power of n, which is simply n multiplied by x raised to the power of n minus 1. On the left side, using the chain rule from basic calculus, the derivative becomes 1 over 1 minus x squared. Notice that our sum now starts at n equals 1 because the derivative of the very first constant term is 0 and disappears. We have effortlessly generated a new infinite series. You might wonder why these properties matter in the real world. In physics and engineering, we constantly represent complex signals like sound waves or heat distribution as infinite series of simple waves through Fourier analysis. To find total energy or velocity, engineers must integrate or differentiate these series. Uniform convergence acts as a mathematical safety permit, allowing engineers to confidently manipulate these infinite sums without getting physically impossible results. To summarize our journey, the properties of a sum function dictate whether an infinite series behaves nicely under calculus operations. We learned that if a series converges uniformly, the sum function inherits continuity from its individual terms. We also saw that uniform convergence allows us to safely integrate and differentiate term by term. These rules ensure that our infinite mathematical constructions remain logically sound and physically meaningful. Thank you for watching.